Exploring Equilibrium with Le Chatelier's Principle, a presentation by Paul Curbelo, Alec Faith, Matthew Larson, and Cindy Myers.
So the purpose of our experiment and our activity was to find out how does the addition of chemicals and a change in temperature affect the system at equilibrium.
In our procedure, equilibrium formed with iron 3 nitrate and potassium thiocyanate. In part A, we added 6 additional chemicals to the system to see what effects they would have.
Stirring now. We saw some color change in there. Cindy, explain. Cindy, explain.
Right now I want to get a homogeneous solution. There's a little bit of...
In part B, we manipulated the temperature by placing the system into water that was heated to 65 degrees Celsius, and also we manipulated the temperature by placing the system into an ice water bath.
Science. Like, science rules. Science rules.
Alright.
Try it.
So me and my boy Matthew here,
Please consider the
we're
following.
working on this experiment right now. You know.
3 minutes have expired.
We found these results. In part A, there was one major overall reaction that we found occurred, and this is between iron 3 ions and the sulfur found in the thiocyanate ion, forming iron sulfate, which is a solid and of reddish color. So we started with potassium thiocyanate, and then when we added the iron nitrate, both of the ions necessary to complete the reaction were there, so the reaction happened and stabilized at equilibrium, which was a reddish color. When we added more potassium thiocyanate, we shifted the equilibrium position further to the right because the concentration of the reactants was higher. So when we added potassium nitrate, there was no change in the position of equilibrium because these ions are not included in the net ionic equation. When we added sodium phosphate, however, the effect was very large because the phosphate reacted with the iron ions, which caused the concentration of the left side of the equation to go down a lot, which caused the equation to shift left towards the side of being clear. When we added back in iron ions with the next molecule, the dark red color came back because the equilibrium position shifted further right with the addition of concentrations on the left side. Finally, when we added potassium thiocyanate, it wasn't enough to change the equilibrium position because the solution stayed clear in the area, but it did have a white perimeter. In part B, we experienced no color change when we heated or cooled the system, but the crystals became slightly smaller in heat.
We got him.
Here we are. It appears
Ladies and gentlemen, we got
pretty
him.
similar, but if you look very closely, the little crystals.
We're gonna shut up.
No, we'll
Hey,
just
Paul, don't move it.
We'll make it like
little
one of those segments where it's
crystals
like Duncan asks the school,
are
hey,
very
ask if this consent is optional, and then like all of the school is just gonna say,
meaning a slight shift left occurred in the system, meaning that the reaction is exothermic because the system would have shifted left in order to absorb energy when it was heated. So the reverse reaction is endothermic, while the forward reaction is exothermic, but not so exothermic that it would cause a change in color.
So after the introductory activity, we moved on to our experiment called Activity B.
Our purpose was to investigate the equilibrium system created by copper and ammonia ions to gain a deeper understanding of Le Chatelier's principle. Our hypothesis was stresses on the ion complex at equilibrium will cause it to shift in order to restore equilibrium as stated in Le Chatelier's principle.
The materials we used for Activity B was an ammonium hydroxide solution, a copper 2 sulfate solution, a hydrochloric acid solution, deionized water, a graduated cylinder, pipette, test tubes, and a test tube rack, and a wash bottle.
Sydney, we got Sydney here. She's
You not commentary over
always
video and
keeping clean. Isn't that right, Sydney?
We're cutting the audio out anyways.
Our safety note. Do not. 1. Try to vape with water vapor off of a hot plate a day.
Welcome to Cool Vape Tricks with Paul. Experiment number 3. How much of this is needed to vape? See, a little bit came. Actually, that really burned my face. Ow. I'm in pain right now. I'm in constant pain. Emotional and physical.
2. Listen to music while performing a lab.
Stand, son, listen, man, dad isn't mad, but how you gonna name yourself after a damn gun and have a man?
3. Act in a lab without consent of your fellow lab partners.
Looks like Matthew doesn't really want to be associated with you.
Looks like Matthew does not consent. I do not consent.
Consent's optional here in science.
That is on film.
4. Take off any safety goggles.
He doesn't have his eye protection on.
Always make sure to.
Oh, it's not C more. Or is it D?
Safety, number 1 priority. Must have.
Being called.
5. Consume lab materials without permission of the teacher.
Walker Bello ate some of our materials.
It fell into his mouth. No, and he swallowed it.
I'm not eating it, just changing my mouth somehow. What are you doing now?
After eating a dangerous chemical, Paul goes to the teacher to ask for it.
No, you don't. No, it's not good. He rinsed it with PG.
He's still on the.
It's literally a food additive. Fine. I mean, theoretically, someone is fine. What's that?
6. Place hand on hot plate.
Paul, stop whacking it as hard as you can.
Okay,
Do vape tricks, Paul.
Just vape tricks, Paul.
I feel like these are a bit self-explanatory though.
Our procedure for Part B was necessary to do under a fume hood for the first part because the ammonium hydroxide is so highly concentrated. So we added ammonium hydroxide to the copper 2 sulfate solution in a test tube, which is viewable on the rightmost picture. Then we divided the solution into 2 test tubes in order for one to be the experimental and one to be the control. We affected stress on the experimental test tube and then compared it back to the control. The stresses we affected were temperature, so we heated the solution with a bath of water heated to 65 degrees Celsius, and we cooled it with an ice water bath. Still.
Okay, so before we did an experiment, we
2
put it
minutes
in
has
the
elapsed.
ice, but we saw no change, and we waited for about 4.5 to 5 minutes. So now we're doing the same with water that's about 65 degrees Fahrenheit. Celsius.
We then added potassium thiocyanate to the solution and also sodium hydroxide, both of which might react with the copper 2 ions.
Is Paul gonna drink it though?
So for our results, we found that there was no change in the complex when temperature was changed.
City, any comments?
It appears temperature has no effect on the system at equilibrium.
From this, we can infer the solution is incredibly stable when either heated or cooled. The 2 different types of stresses did nothing to disrupt the equilibrium. There was also no change in the complex when molecules that react with copper were added, potassium thiocyanate and sodium hydroxide.
Same color.
Paul, turn it a little bit more.
Actually, okay, does it look more blue to you? Does it look more blue?
No, it's
Less
you're,
purple?
you're trying to make it more than it is. It's not enough.
Since the excess of ammonium causes the equilibrium to form, adding chemicals that affect copper will have no effect or very little effect on the solution. However, chemicals which affect ammonium may cause a change, but we are unable to test this because we do not have access to chemicals that affect ammonium.
In conclusion, the complex we formed was reluctant to change when several stresses were applied to it. We could not change the brightly colored liquid in the end.
Oh wait, I'm working as well again. Wait, can we repan that shot?
Out of time.
Hang on. You can't rush time, Paul.
Words from the true master, Alec Fade. Ah, what's that? Nerd.
That's going.
Nerd. If you could give a tip for the lab, what would you give?
Balance the equation.
Yeah, that's a good idea. What is Matthew doing wrong? Is it A, he forgot to balance the equation? Is it animal? Is it B, keep your saliva in your mouth?
Oh, are we doing like
C, not being 5'10".
Question. How optional is consent?
Very.
Don't. That's not going
That's
in.
going on
That's
there?
not-
It's so.
That
good.
I can't believe
bad.
Let's see it.
so
Let's see it. Is
dumb.
it red?
No.
Let's see it.
A little bit red.
my.
It's right there. It's right there. You can see it. You can see it. Feel-
Look at Yarn's face. Look at him. Oh my god.